Welcome to the video for the lab for Unit 10 in Online Chemistry 101. So this week's lab deals with something called reaction rates. We haven't talked about reaction rates in any of the previous lectures, but the basic idea behind them is pretty straightforward. Rate of reaction or reaction rates basically means how fast how fast a reaction takes place, how long it takes to convert reactants into products in a chemical reaction. I may have drawn chemical reactions before in previous lectures, and this is just a pretend chemical reaction where A and B, chemicals A and B, are some pretend reactants, and under the right conditions, A and B get turned into chemical C. And this may or may not have been clear to you, but the speed, how quickly it takes to convert chemicals A and B into something else, into chemical C over here, it can vary. Sometimes there are some chemical reactions where you can convert the reactants into products almost instantly. And there are other chemical reactions where converting A and B into chemical C can be very slow. So I'll give you a couple of examples. And the speed at which the reactants get converted into products is called the reaction rate, which is how fast the reaction takes place. This is a relatively fast reaction. I know it's not balanced, but if you take hydrogen gas and oxygen gas under the right conditions, they will be converted into water almost instantly. This is the rate of this reaction is very fast. In comparison to that, if you take aqueous iron 3 and mix it with, these are called hydroxide ions, with aqueous hydroxide ions, they will make this solid material very slowly. This reaction can take place over the course of years. Some of you may be familiar with this reaction. This is the chemical reaction that causes the formation of rust. So over here, this solid product here is rust. So the punchline here is that some chemical reactions can be very fast, some chemical reactions can be extremely slow, even slower than years for some reactions. And it's not necessarily obvious just by looking at the chemical reaction as to whether a reaction will be fast or slow. Usually you have to perform actual experiments to figure out how fast or how slow a chemical reaction will be to take place. So one thing to point out is that we can actually speed up and slow down reactions as well. So this might be a very fast reaction, but we can tinker with the environmental conditions and actually slow it down under some circumstances. This reaction can be very slow under most conditions, but we can tinker with the conditions that this reaction takes place in and speed it up to some extent. And there are a lot of different ways that you can use to speed up and slow down reactions. I'm going to briefly describe a handful of them. One way to speed up a chemical reaction is to increase the concentration of the reactants. And I'll explain what I mean by that on the next slide, but the idea is that if your reactants are very concentrated, the reaction tends to take place faster than if the reactants are less concentrated. Another classic example of a way to speed up a chemical reaction is to increase the temperature. So usually chemical reactions will take place faster if they take place in a warmer environment than if they take place in a colder environment. So usually heat or warmer conditions will speed up a chemical reaction, and colder temperatures will slow down a chemical reaction. And you're going to do this today. You will also speed up and slow down reactions by altering the concentration of reactants. Catalysts, you won't do this today. However, catalysts we had talked about in a previous unit. Catalysts are materials that are specifically designed to speed up certain chemical reactions. Your digestive enzymes, the enzymes in your stomach, are catalysts that speed up the chemical reaction that is the breakdown of the food in your digestive system. And there are many other things that can speed up and slow down chemical reactions too. But basically the lab that you're doing this week deals with how fast a particular chemical reaction takes place and the ways that you can speed up or slow down that chemical reaction. So the next slide is basically going to describe the chemical reaction. Here is the reaction. You are going to take citric acid, it's going to be aqueous citric acid, and you are going to take solid calcium carbonate. This calcium carbonate is also known as limestone, and basically you're going to mix the two of these things together, and there's going to be a chemical reaction that takes place. Citric acid plus calcium carbonate makes three things. The thing that we are most interested in, the product that we're most interested in, is carbon dioxide gas. So when you mix these two things together, one of the products that they're going to make is carbon dioxide gas, which means that they are this liquid, when you mix this liquid and this solid, the liquid is going to end up bubbling because it's going to be releasing carbon dioxide gas. And because it's releasing carbon dioxide gas, this is a relatively easy way to figure out how fast the reaction is taking place. So you are going to have 5 separate chemical reactions, the same chemical reaction but with slightly different environmental conditions, where the speed of the chemical reaction will either go up or down. And so here's the first test tube. So this is the first chemical reaction. Basically, this blue liquid here is supposed to be the citric acid. That's my cartoon version of the citric acid. And you're going to drop in a small rock of calcium carbonate. So that little shape there, that gray shape, is the limestone or the calcium carbonate that you dropped in there. So you're going to have very concentrated citric acid. You're going to drop in the calcium carbonate, and it's going to start to bubble. And this is going to take place at room temperature. And basically what you're going to do is you're going to use a stopwatch or a clock or a timer on your phone, and you're going to measure how long it takes for all of the carbon dioxide bubbles to be produced. And that is going to be a measure of how fast this reaction takes place. And then this tube here is going to, the amount of time that it takes for all of the carbon dioxide to be produced is going to be your reference. And you're going to tinker with the environmental conditions, and the amount of time that it takes to produce all of your carbon dioxide is either going to go up or down in other environmental conditions. So for example, over here you're going to have another tube. Identical environmental conditions as was shown over here. You're going to use very concentrated citric acid. You're going to use roughly the same amount of calcium carbonate, but this test tube is going to be placed on ice. And because it's placed on ice, because temperature affects the rate of a chemical reaction, the amount of time that it takes to produce all the bubbles should be substantially longer than it took over here with this tube. So this reaction should take place more slowly. Another test tube, what you're going to do is you're going to perform this reaction at room temperature, but what you're going to do is you're going to reduce the concentration of citric acid. So you're going to use the same volume of liquid, but there are going to be fewer citric acid molecules floating around in this liquid. And if there are fewer citric acid molecules, you're only going to be using 60% citric acid. Excuse me. If there are fewer citric acid molecules floating around in here, then the idea is that they are less likely to bump into this calcium carbonate. If they're less likely to bump into the calcium carbonate, they will produce carbon dioxide more slowly, and so this reaction should also take place more slowly. This reaction is a little bit stranger. You're going to use not a test tube, but you're going to use a 50 milliliter beaker. So it's going to be sort of a wider space that the reaction takes place in. And in this case, you're not going to use a little stone of calcium carbonate. You're going to use pulverized calcium carbonate. So it's going to be powdered calcium carbonate that's going to settle at the bottom of this tube, and you're going to use relatively unconcentrated citric acid. Now, at this point, I don't even know whether the rate of this particular reaction is going to be faster or slower than the rate of this particular reaction. And there are 2 reasons for why I don't know what's going to happen. The first reason is that you're using very diluted citric acid. So there won't be many citric acid molecules running around in here. They will be less likely to bump into the calcium carbonate, the pulverized calcium carbonate down here on the bottom. So on the one hand, because this is diluted citric acid, the rate of the reaction should be slower than the rate of this reaction. However, you're not using a solid rock of calcium carbonate. What you're using is calcium carbonate powder or pulverized calcium carbonate. Because of that, the citric acid molecules that are in this blue liquid here are more likely to, they have more of a chance to bump into more calcium carbonate molecules because this is pulverized. The way to think about that is that even though there are a lot of citric acid molecules floating around in this liquid, the fact is that they cannot penetrate to the inside of this rock very quickly. It takes them a while to eat away at the outside surface of this calcium carbonate rock, and over here, because this is pulverized, even though there are fewer citric acid molecules, they have more access to the inside of this container because it is pulverized, and they can, the citric acid molecules can sort of float in and insert themselves inside, in between the pulverized pieces of calcium carbonate. So on the one hand, because there is not much citric acid in this container, you would think the reaction would take place more slowly. On the other hand, because the calcium carbonate is pulverized, those citric acid molecules should be able to access more of the calcium carbonate molecules, and the reaction should take place faster. I have no idea which one wins out in this case. Does it take place faster than this reaction or slower than this reaction? I don't know. You're going to have to do it to find out. And then the final chemical reaction is to use the same conditions that you used in this original tube. You're going to use 100% or highly concentrated citric acid, and you are going to drop in a rock of calcium carbonate. But under these circumstances, you're going to take this test tube and put it in hot water. And presumably, because this reaction is taking place under warmer conditions, it should produce the carbon dioxide much faster than the carbon dioxide is produced in this original test tube. So this should be fast, this should be slow, this should be slow, and this middle one, I haven't the foggiest idea what's going to happen. I guess I'm going to go home and figure it out myself. So that is a summary of this week's lab.